if I know the voltage and the charge, how much energy is involved? And if I place a point charge in space, how charged up is this location? So first, I will introduce to you the electron volt. The electron volt is EV. And why does it exist? Because joules, which is the unit of measurement for energy and work, J, is huge. It's way too big for electrons. So we define a smaller energy unit, the electron volt. It's defined as this. So 1 electron volt is the energy gained by 1 electron moving through 1 volt. Does that make sense? I'll say that again. 1 electron volt is the amount of energy gained by an electron moving through 1 volt. And it's equal to 1.6 times 10 to the power of negative 19 coulombs, which is the charge of an electron, multiplied by 1 volt, which gives you 1.6 times 10 to the power of negative 19 joules. There's also kilo EVs, which you might see. So that's it for the units. But I'll tell you, the electron volt is not an SI unit. So if you know the global SI system used across science, kilograms, meters, seconds, things like that. The electron volt is the first unit I've covered on this channel that's not part of the SI system. You must convert back to joules if you're solving with mass and speed. You cannot use electron volts as a unit in the SI system. I'll write out some formulas that we've been looking at in the past few videos. So the change in potential energy measured in joules is charge times V. And to convert it into electron volts, it's equal to your charge in E times volts in EV. So before we move on to the problem solving part of this video, what if we want to know the potential, and potential is energy per coulomb, at a distance r from a point charge? This is the formula that you would use, which I covered before, but it's 1 over 4 pi, this symbol, times charge over distance. Here, V is just a scalar. So a scalar is just a number, there's no direction. It's not a vector, like speed versus velocity. Velocity has a direction, speed is only magnitude. The sign of V, so positive or negative, is equal to the sign of the charge, Q. The closer you get to the charge, the higher the potential for a positive Q, or more negative for a negative Q. What's the difference between electric field and electric potential really quickly? So here's a concept comparison. Electric field is given with K charge over R, with K being Coulomb's constant. Right here's the electric field equation, and it depends on distance squared. But electric potential depends on just distance linearly. So with electric field, if you move 2 times as far, it would be a 1 over 4 change. 3 times would give you a 1 over 9 change. But with electric potential, it's linearly proportional. So electric field will drop off faster than electric potential. Here's an example problem. Our goal is to find the electric potential as 0.4 meters away from 1. A positive 15 microcoulomb point charge, B. a negative 15 microcoulomb point charge. Use the formula, which is on the free cheat sheet. It's V equals Coulomb's constant times your charge divided by distance. Coulomb's constant is 9 times 10 to the power of 9. And your charge, it's in microcoulombs. But simply to convert to normal coulombs, you just have to times by 10 to the power of negative 6. So it's 15 times 10 to the power of negative 6 coulombs divided by our distance 0.4. And we can just change the sign in front to find both values. And it becomes plus or minus 3.38 times 10 to the power of 5 V. Simply positive if it's positive and negative if the charge is negative. How about another more advanced problem involving work? If you're moving a 2 microcoulomb charge from far away over here to a position that's 0.3 meters away from a positive 10 microcoulomb source, how much work does this move take? The formula for work in this case is charge times the change in voltage. And since voltage is given with KQ over R, the new formula we've been looking at in this video, and the volts don't change, so there's no difference, then the work formula becomes KQ over R, with this Q being our smaller thing and big Q being the source. Plug in our values, and you get roughly 0.6 joules of work required to make this move happen. And electric potential, like I said, is a scalar. So we can just add it. You don't have to worry about direction. It's a scalar. So here's the problem. We're going to try and find the electric potential at 2 points A and B. And I've written out the 2-point charges. You're told this, their positions and distances. So point A, the distances from Q1 and Q2 are 30 centimeters and 60 centimeters. We're not even going to draw this out. I'll show you why soon. The distance from point P to Q1 and Q2 are equal distances, so 40 centimeters, to both. So this is A to Q1 and to Q2. This is B to Q1 and Q2. This is where electric potential is easier than field. Electric potential is not a vector. You don't have to do vector addition, no direction, no trig, just add with signs. So let's find the electric potential at A and B. At point A, it's equal to K, and I'm going to show you a formula here. We did talk about in a previous video, and it's written as this, but what's important is that we can just drop in numbers now. K is a constant, and we multiply this constant by Q2, which is positive. I'm not going to write this out because I'm running out of space, but positive Q2. And the radius from Q2 to position A, which is 60 centimeters, but I'll be honest here, but I think I may have made a mistake. I think this 6 and 3 were meant to be swapped. It doesn't matter. Our problem still proves the point. So 30 centimeters away plus Q1 over the distance from A to 1, which is supposed to be 6. I'm sorry about that. And the charge of Q1 is negative. So negative Q1. I guess just Q1 over 0.6. Answer is roughly, I say roughly because of course our number mismatch, 7.5 times 10 to the power 5 V. That's the electric potential. And how about at point B? At point B, since the charges are at the same distance, so 40 centimeters, it's an equal distance, but they're opposite in sign. So it equals to 0. You can try it with the math, it's equal to 0. Of course, this formula is on the free cheat sheet in the description as well. So at point B, there's 0 potential. And at point A, there's this much potential. That means the net potential is a positive. But let me clarify, there's still an electric field at point B. Even though the potential is 0, the field is not. Why? Because the electric field is a vector, and the fields from the charges point in the same direction. But there's just no potential. This is where potential is 0 is called an equipotential surface. Let me write that out. Equipotential surface. And what an equipotential is a surface with constant V. That's all. I'm not going to go into that because it's a very quick topic and I don't want to waste your time.